Greetings, my name is MathYou, and in this video we're going to multiply polynomials. All sorts of different types of polynomials. We're going to do monomials times binomials, and binomials times binomials. I think there might even be a trinomial times a trinomial. So we'll talk about a couple of different techniques to make sure that you're able to do all this multiplication successfully. Let's have a look. The very first task we see in number 1 is to multiply a monomial times a monomial. And remember that a monomial is a polynomial that only has one term. And so you're seeing that. Let's make that a little larger. There we are. So we're seeing only one term inside these parentheses, one term inside these parentheses. Let's do just a little quick multiplication. And since it is all multiplication, we can move these things around. And when I say these things, I'm talking about the -2 is its own thing. It's a factor because it's connected to the x to the third by multiplication. And the 3, which we have been recently calling a coefficient, is connected to the x to the 7th power. The 3 and the x to the 7th power are connected by multiplication. So we have, in one way, we have 4 factors that we're looking at here. So we can shuffle them all around, and I'm going to do that. I'm going to really think of this as -2 times +3 times x to the third times x to the 7. And then I'll do the multiplication, multiplying those coefficients that I've now put next to each other, still separated by multiplication, and we'll get -6. And then multiplying like bases to their respective exponents. We've got x to the third times x to the 7, and we know that when it's multiplication with like bases, we can add the exponents and we get x to the 10. And that's our final answer. There is, as I mentioned in the previous video, this property called the distributive property. And more specifically, we're distributing multiplication over addition. And you'll see in problem number 3 that we're actually going to be distributing over subtraction. But generally speaking, distributing over multiplication tells me that I can take this a and multiply it to the b and send that a over here and multiply it times this c value. So let's try that in number 2. The 4x times the -5x, and we'll think of it just like that. How much space do we have? Maybe just enough. I'll take the 4x and multiply it by the -5x. So I've distributed to this first term. And then I'm going to bring the plus sign over. That's this plus sign is now here. So plus, and then we'll take the +4x and we'll multiply it by the +8. And then we can clean this up a little bit. The 4x times the -5x, the 4 times the -5 gives us -20. The x times the x gives us x squared. And then in our second term here, the 4 times the 8, 8, 16, 32, it's a +32. And then we only have one multiple of x. So for some of you, it's going to be very beneficial to do that in a very slow and organized way to make sure that you get all those factors to come along with you on your way to a final answer. Number 3 is very similar to number 2. We're just illustrating that you can distribute multiplication over subtraction also. In this case, we're also multiplying a fraction, so we're distributing a fraction, and we're distributing our variable to a 2nd power, so that is allowed. So let's start our distribution here. Let's shorten it up a little bit. Let's say the 1/2 times the 8 gives us a 4. The x squared times the x gives us x to the third, because there's an x to the 2 and there's an x to the 1. We're multiplying, so add the exponents, we get x to the 3. And then the minus sign. And the 1/2 times the 20 is a 10. And there are no other x's other than the ones that we're distributing with the x squared. So we end up with -10x squared. I hear a visitor at the door. Hello? Are you there? Did she sneak in? I don't see. Oh, she did sneak in. She's sneaky. Hey, Snoop, come over here. You want to say hello? Or you just want to play with all of my things on my desk? Oh, baby. Such a baby. All right, what do we need to look at next? So the distributive property is also used to multiply polynomials with more than one term. So you see that what I'm distributing here, she doesn't want me, she just wants to push buttons on my equipment and try to flip over the computer, and she's going to walk on the iPad, of course. Sophie, she's sitting on it now. You're so helpful. Get out of here. Keep going. Keep going. Thank you. Sorry about that. Okay, so we can multiply or distribute this binomial into another binomial. So we can multiply that 2x plus 5 times the 4x, and we could do 2x plus 5 times the negative 7. There's a shortcut, however, and I'm not even going to show you doing it that long way because we're never going to do it that way ever again. Sophie, you can't do math. Just say hello. Just say hello. Very good. Okay. Go attack your sister. Let's talk about the shortcut right away. And the shortcut, as a lot of you know already, is called foiling. F-O-I-L. The F stands for firsts. So I'm going to take the 2x and multiply it by the 4x. The 2 times the 4 gives me an 8, and the x times the x gives me an x squared. The O stands for outers. So the 2x and the negative 7 are sort of the outermost factors in the 4 terms that we're looking at, the leftmost and the rightmost. So 2x times negative 7. The 2 times the negative 7 gives me a negative 14. And there is a multiple of x on the 2, so we have to bring that along, so minus 14x. And then the I in the foiling process stands for inner. And these two middle terms are the inner terms. So a positive 5 times a positive 4 makes positive 20. And there is a factor of x on the 4, so we'll bring that along, 20x. And then the L in foiling stands for lasts. So the last term in each of those parentheses, that's the positive 5 and the negative 7. You multiply those together, you get negative 35. So that is the result of F-O-I-L, the foiling process. And then we do need to do one more thing here. We need to combine like terms. That's not always possible, but in this case, we can combine like terms. The middle two terms, the O and the I terms, have the same variable, and that variable is being raised to the power of 1, so they are like terms. We're going to keep the 8x squared. Negative 14 plus 20 makes a total of positive 6x's. And then we bring along our constant term at the end of minus 35, and we've got 8x squared plus 6x minus 35. You've just multiplied two binomials using the foiling technique. Problem number 5. I don't know that I've ever heard a technical term for it, probably because foiling is really a shortcut anyway. Technically, we should be able to take this x plus 4 and distribute it to this term, and to this term, and to this term. Instead of doing that, I like to do what I call superfoiling. Each term has to be multiplied by each term. So this x is going to get multiplied into this first term, and the second term, and the third term. And the plus 4 gets multiplied into the first term, and to the second term, and to the third term. So at the end of this first stage of this process, we're going to end up with 6 terms. And then hopefully, if we'll be able to combine like terms and consolidate it a little bit. Let's see what we get at the end of the first sort of phase of this process. All right, let's do this. X times 2x squared makes 2x to the third. And then we take the x and multiply it by negative 3x. So there's a negative 3 and a couple of multiples of x, so that makes x squared. And then the x multiplies way out here to this negative 2. That's negative 2 times x is negative 2x. So we took the x and we distributed it to all of the terms in the next set of parentheses. Now we're going to take the positive 4 and multiply it to all of the terms in that next set of parentheses. So 4 times 2x squared makes a total of 8 x squareds. The 4 times negative 3x, 4 times negative 3 is negative 12, and there's that multiple of x. Bring that along. And the positive 4 times a negative 2, positive times negative is negative, 4 times 2 is 8. And there are the 6 terms that I promised. Can we combine like terms, CLT? Do we see any more cubes? I only see this one third degree term. Can't combine it with any other like terms, so let's write that one down correctly. 2x to the third. Are there any second degree terms? There are. Here's a negative 3 x squared plus 8 of those. Negative 3 of them plus 8 of them makes a total of positive 5 of them. Them what's? Them x squareds. Don't know what they are, but I've got 5 of them. I'm a lucky guy. What about first degree terms? Any x to the first powers? Sure enough, there's minus 2 of them and minus 12 of them. Negative 2. Take away 12 more, and we have negative 14 x to the first power. And constant terms, there's only this one at the end of a minus 8. My 8s and my g's look so similar. I used to make my 8s like snowmen, just 2 circles, one on top of the other. And then I realized that my handwriting is so bad, they kind of looked like drunken snowmen. They were kind of falling over and kind of lousy looking. So I started trying to do my 8s like this, but boy, my 8s and my g's look too much alike. So I'll keep narrating what I'm doing, and I'll try to never write an 8G. All right, so that is a superfoil plus a combine like terms. And then we have some special cases that we should look at. The first is called the difference of squares. And what you're seeing, well, since it's called the difference of squares, let's look at this side first. A squared maybe ends up being x squared. And b squared maybe ends up being 25. So the point is that x squared is a perfect square because it's the result of having squared an x. And 25 is a perfect square because it's the result of having squared a 5. So if I've got a square minus a square, I would say that that's the difference of 2 squares. What's the difference between 5 and 8? How about 3? How'd you get that? Subtraction. So difference means subtraction? Absolutely. Most of the time. Is there multiplication that we could do that after we combine like terms would result in a difference of squares? And the answer is yes. If you take a plus b and you multiply it by a minus b, the result is a squared minus b squared. What happened to that middle term? Take me back to this foiling process up here. I took an a plus a b and multiplied it by a c plus a d, and I had these 4 terms from the foiling process, and then I combined like terms, and I got to 3 terms. And my video is frozen. That's not cool. Why is my video frozen? Oh, then I just moved it, and it starts moving again. That's not good. How much farther do we have to go? Let me try closing a couple of other applications on the computer to make sure they're not interfering. Let's close this one. And let's close this. What else can we close? Let's close this. All right, maybe that'll help. So it is unusual that when you take a binomial times a binomial, that you would end up with another binomial like a squared minus b squared. But that's why it's called a special case. It's kind of special that that happens. Another special case is when you take, and I'm going to draw another line through here. When you take a plus b and you square it, remember that squaring means multiplying it by itself. A plus b times a plus b. You end up with an answer that looks like this. When you take a minus b and square it, which means a minus b times a minus b, the result looks like this. Those two results look awfully similar. The a squareds are there, the 2ab is there, the b squared is there. There's only that one little difference of the minus sign and a plus sign. So let's look at a couple of examples of these. In number 6, this is an example of a difference of squares. This is the a plus b, and this one's the a minus b. Their order has been changed, but that's okay. It ends up being equivalent. And if we FOIL, the 5x times 5x gives us 25x squared. The 5x times the positive 1 gives us positive 5x. I'm FOILing now. The O, negative 1 times 5x, gives me a negative 5x. And the negative 1 times the positive 1 gives me a negative 1. So I FOILed. And then I'm going to combine like terms if I can. I can. These two terms, the O and the I terms, combine to cancel out, which is very unique. And the result is 25x squared minus 1. Now what I'd like you to realize is that 25x squared is equivalent to 5x squared minus the 1 that you're seeing here is the result of 1 squared. So I want you to see that this pattern matches with this pattern. My a value was a 5x, and if I square it, I get my 25x squared. And my b value was a positive 1, and if I square that, I still get 1. And if I put a minus sign between those, I end up with my a squared minus b squared, which in this case is 5x squared minus 1 squared, which when you simplify that and do that little bit of multiplication, you get 25x squared minus 1. So it's a shortcut. You can, if you get the hang of this pattern, you'll realize that you don't even need to create these O and I terms because you're going to know in advance that they're going to cancel out every time. Now, how am I supposed to look at this original problem and know that if I FOIL it, the O and the I terms are going to cancel out? And then instead of FOIL, I can really just do FL and skip the O and the I. The way that I can tell is that, for one, it matches this format of a minus b times a plus b. Look at these two parentheses here. What's the only difference between this set of parentheses and this one? The only difference is that one's got a minus sign and one's got a plus sign. That's the a minus b, a plus b, or vice versa, a plus b times a minus b. You'll learn, again, although I'll tell you right now, that when you have binomials that match that format, a minus b and a plus b, those are called conjugates. A a minus b and a plus b are conjugates. And when you multiply conjugates, those two middle terms, the o and the I terms, are going to cancel out every time. I've made a mess of this page. Let's come over here and look at number 9. Here we're taking something in parentheses and we're squaring it. And I'm just going back over here to look at this. Is the number, let's say 49. Is the number 49 a perfect square? I think you'd say yes. And then I would say, why? Why would you say that that's a perfect square? And you'd say, well, it's 7 squared. And then my follow-up question is, can we rephrase it just a tiny bit? Can I say that 49 is a perfect square because it's the result of squaring something? Sure, it's the result of squaring something specific. It's the result of squaring a 7. But generally speaking, a perfect square is the result of having squared something. Okay, well, what about this? Is this that I've just highlighted a perfect square? By our new definition, it is. Why? Because it's the result of having taken something and squared it. Therefore, a squared minus 2ab plus b squared is a perfect square. How many terms do you see in there? Well, the a squared is a term, separated by a minus sign from the 2ab, which is its own term, separated by a plus sign from the b squared, which is its own term. Therefore, there are 3 terms. And what do you call a polynomial that has 3 terms? You call it a trinomial. Therefore, this thing that I've highlighted here is a perfect square, and it's a trinomial. So I think we should call it a perfect square trinomial. It's not all that creative, but at least it makes sense, right? Okay, so a perfect square trinomial is the result of having squared a binomial, in this case. And here is a binomial, and we're going to square it. Should we use the foiling process? Should we set it up as 3x minus 4 times 3x minus 4? You can, or we can use this kind of shortcut that we're seeing up here that tells us that when we're squaring a binomial that has this sort of a minus b format, that we can write the solution a little bit more quickly. We'll take our a term, which is the 3x, and we'll square it, and then we'll subtract a pair of ab's. A is 3x, b is 4y, and do I have room over here? Just barely. We're going to add our b value, which is 4y, but we have to square it. Make sure your 4's and your y's are distinct. There we go. Okay. And now we have to clean this up. 3x times 3x makes 9x squared. And then I've got a negative 2 times a 3 times a 4, which is negative 24. And there's a multiple of x and a multiple of y, plus 4y squared. That's 4y times 4y, which is 16y squared. Could I have written this out as 3x minus 4y times 3x minus 4y, gone through the foiling process, and combined like terms? Absolutely. Would I have gotten the same answer? Absolutely. What is this thing called? It's a perfect square trinomial. What if I had to do this backwards? What if someone gave me the perfect square trinomial and I had to sort of reverse engineer where it came from? Would that be easy enough? Well, first you'd have to identify it as a perfect square trinomial, which I can show you how to do. This thing is clearly a perfect square, the 9, And this is very obviously a square because it says x squared. The 16 is pretty evident as a perfect square. It's 4 squared. And the y squared, again, is obvious because it says y squared. So those things are both looking pretty square. What's the square root of 9? What's the square root of 16? What's 3 times 4? 12. Double that. See that 24? See this 24? That's a good indicator that you're working with a perfect square trinomial. If the square root of this times the square root of this doubled equals your middle term, you're working with a perfect square trinomial. What's the square root of this? How about 3x? What's the square root of this? How about 4y? All of a sudden, it's pretty easy to reverse engineer. It takes a little bit of practice. First, you have to identify that it's a perfect square trinomial, and then you have to know to take the square root of the two things and put them into the parentheses. And how do you know to separate them by a minus sign right here? It's this minus sign. You work with enough of these things, all of a sudden the mystery becomes unraveled and you see these and they just correlate pretty quickly. But just so you know, we're not going to be doing this right away, reverse engineering the binomial squared. We're going to keep working our way from left to right, doing the squaring and trying to practice the shortcut. But at some point in time, I am going to ask you to reverse engineer this. I'm going to give you the perfect square trinomial and ask you to recreate this thing. And when we do that, we'll call it factoring. But we're not going to do that just yet. But just wanted to give you a little preview. All right, so that is an example of foiling the product of two conjugates, which results in a difference of squares. You'll be asked to reverse engineer that process eventually also, and an example of creating a perfect square trinomial by taking a binomial and squaring it. I think that's about enough of that for now. Let's take a little break, and I'll see you again real soon. Thanks.